So, according to sector, this is all we're doing today. So we just see how we go with it. If we find it pretty easy, we can move on. But that's our plan for today so far. Pre-A composite functions. So that word I was just asking you, where does it come from? So what we have with composite functions is we have one function composed of another function. Okay? You might also remember back to when you're doing Year 9 math where you have composite shapes. Alright, so an example of a composite shape is something like this. It's a shape composed of two rectangles, and we can break it up into its requisite components and so forth. So that's why it's called that composite functions. And just in terms of notation, like if we have f of g of x, this is the notation SACE will use. However, the textbook, as it was written for a couple of different curriculum, they sometimes use this odd notation, f circle g in brackets of x, and they'll sometimes use that last notation as well. And all of those mean the same thing. And then with an arrow, all right? It means you're putting g of x into f of x. Okay, you're substituting g of x into f of x. So we're pretty familiar with composite functions, I suspect, but the trick here is that we're going to assess both the domain and range of composite functions. Okay, so we're drawing on that skill of domain and range we learned in 11 methods, and we're drawing on the skill of composite functions, which we also covered in 11 methods. So we have f of x is the square root of x, and g of x is 2x take 3. So they're the two functions that we have here. Part A, find f of g of x and state its domain and range. So f of g of x. So what that means, I'm taking g of x and it's going inside f of x. So I'm putting this whole thing everywhere there is an x in f of x. So f of g of x then will be the square root of 2x take away 3. Alright, that's the function we've got. Now from here we could graph it in order to assess its domain and range. But let's see if we can answer it algebraically, alright, using what we understand about functions. So we have the square root of some number, and we know in order to graph this on the Cartesian plane, the inside here has to be greater than or equal to 0. We can't square root a negative number. So the domain then is 2x take 3 must be greater than or equal to 0. And we're going to go through and solve this inequality. Now, we're going to be solving inequalities a fair bit in spec, and the way they work the exact same as equals, all right, except when you multiply or divide by a negative, the inequality will switch directions. Now, you don't have to remember that now, it will pop up in future lessons, probably today. So we'll just go through and solve, and we have x is greater than or equal to 3 on top of 2. So that's our domain. Now, for the range, okay, where we took, so domain is possible values of x, right? Range is possible values of y. For the range, you just think about what happens as x tends out towards positive infinity and negative infinity. What's happening to the y value? So as x approaches positive infinity, as x gets super large, like if you put 1 million in there, all right, you're going to have the square root of 1 million. Y gets super large as well. So y is approaching infinity as x approaches infinity. If we talk about going in the other direction, we have negative infinity. We're going to have the square root of a negative number, so it doesn't exist. All right. In fact, when we talk about the square root of x function, if I graph it, this is what the square root of x function looks like. All right. Can anyone tell me why wouldn't it look like this? Why don't we graph that as a function?
Because it can't be negative.
But hang on, if we've got x is 4 here, and we have y equals the square root of x, and so that means I would have the square root of 4, and I would have plus or minus 2. I would have 2 answers, right? Which is like technically correct as far as square root goes. There's 2 reasons. The first is that it's got to do with what we've defined, and the second reason is that that's not a function, is it? What do we call this? Relationship. Yeah, it's a relation between 2 variables, and we will deal a lot with relations as well. A function has, each x value has one unique y value. Here we can see it doesn't pass the vertical line test, right? It's a relation. So that's the first reason. And the second reason is we have y equals the square root of x. That's the function we've defined. Now, what this technically means is we're graphing y equals the positive square root of x. All right? If we wanted both, we would graph y equals plus or minus the square root of x. All right? In the question, we don't have anything written out front, so we assume the positive circumstance. Okay? All right, so unless it's got negative there, you always assume the positive there. Now, this is what the function looks like. And what we can see is that it only exists for positive values of y. We don't have negative values of y. So for our range, we're going to say y is greater than or equal to 0. It exists at 0. You can have the square root of 0, but it doesn't exist for values less than 0. Now, just to be clear, this is the graph of this function. This one's going to be the same, but shifted over a little bit. So you can use your calculator, graph both, and they will help you out there. Okay, that's our first one. Let's talk about our second one, which we have is find g of f of x. Okay, this time we're taking f of x, that whole thing, and putting into g of x. That's going to give me 2 times f of x, and then take away 3. Okay, so for the domain, all right, the only constraint we have is that this x has to be positive, doesn't it? So for the domain, we say for part B, x is greater than or equal to 0. And for the range, like we can break this down into its components, right? We know that the range of this part is y is greater than or equal to 0, but the whole thing's been shifted down 3 units. And so the range is y is greater than or equal to minus 3. All right, so if you're going to graph this function, it'll look something like this. It'll have y is minus 3 here, and it'll follow this shape. It'll just go that way forever. So from there, we can see domain exists for positive values of x, range values of y larger than minus 3. All right, all good so far? So it's about using what we understand of the functions and our calculators to help us out. All right, let's move on to C. Now we've got cos of x function. So in C we have p of x equals cos of x. Okay, find f of p of x. F of p of x. So we're putting this function into f of x, and f of x I've erased, it was the square root of x function. So if I put cos of x in there, we're going to have the square root of cos of x. Okay, so we can graph it and look at it, but let's think about it algebraically, right? We know that this component has to be positive. Cos of x has to be positive. And let's think specifically about the cos of x graph. Okay? So we're getting to a stage where I expect you guys to sort of know what the cos of x and sine of x graph look like. If this is a Cartesian plane, we'll just draw it from minus 2 pi to pi. Cos of x starts at the top, okay? And we have one wavelength there, and we have one wavelength in this direction as well. Now, and then if we're putting these roots in, cos of x is 0 at pi on 2 and minus pi on 2. I'll justify that with the Cartesian plane for you now, with the unit circle. So, if this is our unit circle, right, cos of x is the x values, and the x values are 0 here and here. So that's an angle of pi on 2, that's an angle of 3 pi on 2, right? So we have roots at pi on 2 and 3 pi on 2, and then multiples of 2 pi, all right? So 2 pi this way will be that root. 2 pi again this way will be a curve again. 3 pi on 2, that's the second root. Okay, 2 pi units that way gives us that root. Okay, you can see it repeats itself over and over. So they're the zeros. All right, now we're performing the square root of cos of x, which means we can only have positive values of y. Okay, we can only have positive values of it. So we're rejecting, or these ones are outside of the domain, aren't they? And you can see it's going to be periodic. We're only going to have we're going to have a domain that's periodic. We can perform the square root of that part. We can perform the square root of that part. We can perform the square root of that part. But we can't perform the square root of this part in here. So how might we answer it? Does anyone have any ideas? Firstly, let's just say, where does it exist? Okay, where does it exist in our first? Where's the first arc that it exists for? So we can perform the square root of it here. So that part there has a domain of minus pi on 2 to pi on 2. All right, so that'll be the first part for the domain, minus pi on 2 to pi on 2. All right. And then, how far along is the next one going to occur? 2 pi. So you're correct, the distance from there to there is pi, but they're not the same root. If we just add pi, then we're going from there to pi. So we have to add 2 pi because we're going from there to there. That's where the arc next begins to occur. Plus k to pi, where k is an integer. Look at that beautiful font there. Plus k to pi for all k is positive and negative integers because we're going in a negative direction as well. So that's quite tricky, right? Now I would anticipate if you were answering this, you'd be okay to sort of get that first part, all right? And if you graph this function, it will look a little bit like this, although it'll be flatter towards as it gets closer to the roots. But you'll be able to see, okay, it's existing here, it's existing here, it's existing here. It's periodic because it's a cos of x function, so I need to come up with some way to describe it. All right. So that's the domain for that one. Any questions about that? That's probably our hardest one so far. Okay, how about the range then? The range is the square root of the cos of x. All right. Now range is talking about what are the possible values of y. Now the smallest cos of x can be the smallest non-negative value. Smallest, that's the largest. What's the smallest non-negative value that cos could take? 0. Okay, cos can be 0, and the square root of 0 would be 0. So the lowest value of y then is 0, and the highest value that cos can take is 1, and the square root of 1 is 1. So isn't that fantastic? Like we can just look at that and reason to, this is the domain, this is the range, well done. Graphing it on your calculator, observe it, and confirm what you've got there. All right, on to our last one then. We have D, and D, we have Q of x is 1 on x. Find Q of G of x. So G of x was 2x take 3. So we've got Q of G of x. This time we're putting the Q of x function, the G of x function, into Q of x. All right, we're putting that one into here. We'll have 1 on 2x take 3. Okay. Now this is a good point to remind us of what we have here is a rational function. A rational function. A rational function because we have stuff at the top and stuff at the bottom. Now the properties for a rational function, we're sort of going over in methods at the moment, but I'll just define it like this. This is really important that we remember this. If we have u on top of v, all right, f of x equals 0 when u equals 0. And f of x is undefined. Undefined. When? Very good. All right, so that's going to pop up. All right, definitely in methods at the moment, going over the quotient rule, pops up there, and it's sort of assumed knowledge from now on. So that means this function, its roots occur when 1 equals 0. It has no roots. It's never going to equal 0. All right, but it will be undefined. So undefined when 2x take 3 equals 0. So we'll have 2x is 3, we'll have x is 3 on 2. And so that means for the domain is going to be any value of x except this one. Alright? So for the domain, we'll say x does not equal 3 on 2. That means it's every other real number except 3 on 2. And then for the range, okay? Now, for the range, we do have a horizontal asymptote as well. Vertical asymptotes are very easy to test for. Vertical asymptotes will always occur when the denominator is 0. Okay, we have a vertical asymptote there, right? That invisible dotted line going down. Horizontal asymptotes, we need to sort of say what's going on here. What happens as x gets really large? Okay, again, you think about if I put 1,000 in here, let's make the argument. I've got 1 on 2x take 3. As x approaches positive infinity, all right, if this gets really large, I'm going to have 2 times infinity. I've got 2 infinity, that's enormous. So if I have 1k divided by 2 infinity people, everyone gets pretty much
Nothing.
0. Yeah, pretty much 0. So as x approaches positive infinity, this component, 1 on 2x take 3, this whole thing is going to approach 0, but from the positive direction. Okay? It's getting close to 0, but it's still positive. It's a positive almost nothing. Alright? What about as x approaches negative infinity? Okay? So if I put minus infinity in here, we've got minus 2 infinity and then take away 3. We've got a super negative number. 1 divided by the super large number is pretty much 0. But because it's negative, all right, as x approaches negative infinity, this component is approaching 0, but from which direction? From which side of the Cartesian plane? Below. So it's approaching 0 from the negative direction. So if we think about that, if I've made this argument up here, we haven't graphed it yet, but if we think about what's going on, all right, as x approaches negative infinity, it's approaching 0. See how it's getting closer and closer to 0 here from the negative direction, all right, from below. And as x approaches positive infinity, as I'm going in this direction, it's approaching 0 from the positive direction. What do we have going on there at y equals 0? Horizontal asymptote, all right? And so we can see it exists for all other values of y except as it approaches 0. So the range for D, we make the range, y does not equal 0. It exists for every other value. Now I'm going to float around and show you how we can use our calculator to determine that. What we'll basically do is graph it, zoom right out and trace along it. And you'll see that it's approaching these limiting values, okay? And we have a vertical and horizontal asymptote there. All right, how do we feel about this exercise?
Cheese.
All right, so yeah, cheese, nice. So use a bit of algebra where you can, but I do encourage you to use your calculator in support, and I'll come around and show you guys individually how to do that now, I reckon.